Okay, so welcome back to part 2 of the video. And so what you can see is I've just copied and pasted in the graph from the calculator onto the sheet over here, and it's got all the key parts. What I'm going to do now is go ahead with example 2, and hopefully you have attempted this on your own, and now I'm just going to go through and show you the key answers to each of these. Okay, so a football is punted in a parabolic flight path. Once again, this is the part that allows us to use quadratic functions. The height in feet of the ball t seconds after being punted is modeled by h of t equals minus 16t squared plus 45t plus 2.5. As before, the height h is essentially y, t is essentially x, and we're going to go ahead and graph that. So what I'm going to do over here is add myself a graphing page, and so I'm just going to enter the equation directly in. So let me just give myself a little bit of space here. So I have negative 16 t squared. Of course I'm going to use x as I did before. Let me just see, no, I don't want the caps on. Negative 16x, there we go, squared, plus 45x plus 2.5. I'm going to go ahead and hit enter. As before, you potentially have a problem with the window depending on the graph and whether it's going to fit into a standard window. So what we can see here is that it goes up and comes back down pretty quickly. So we're going to modify the window a little bit. I need to increase the maximum and then just modify the x-axis a little bit. And so once again, I'm going to use the window settings. I'm going to go from -2 to about 6 based on what I've seen on the graph so far. I'll leave my y minimum as -5, but I'm going to increase the maximum to at least 50, and let's see how we go. Okay, and so that's a little more accurate picture of what we want. I'm going to take my equation label or name and just try and shift that out of the way a little bit. Okay, so if we come back to the question, as before, we've been asked to find and label the vertex and also the y-intercept. So we'll do that over here. Menu, I'll use the trace function, and I'm going to trace the graph. Just scroll along there. So there's my y-intercept, which is occurring at 0, 2.5, and then I'm going to escape out of there and then use the calculator to analyze graph, and once again we have a maximum left bound, right bound, and there's our maximum, and so there we go. And what I might do as well is just shift that graph a little bit up so that I can see that a little bit better. So there's my y-intercept at 0, 2.5, my maximum at 1.4, 34.141. So here's our first question. What does the y-intercept represent? Well, keep in mind, similarly to the aeroplane question before, essentially the y-intercept occurs when x is 0. Of course, x in this case is time. And so when time is 0, in this case, we had 2.5, which was h of t, which is of course the height. And so if we interpret this in the context of the problem, the answer is this is the height at which the ball was kicked or punted. Because you can see from the context of our question, a football is punted if at time 0 the ball is already at 2.5. Of course, this is where it is dropping out of the player's hands and he or she is about to kick the ball. Okay, what is the maximum height that the ball reaches, and at what time, after how many seconds, does it reach the height? Of course, we've already established this from the graph. It's the coordinates of the vertex, and so at what time, 1.41, if we round to 2 decimal places, 1.41 seconds after it's been kicked, it reaches a height of 34.14 feet. Okay, as the ball descends, it is caught at a height of 5.5 feet above the ground. Once again, remember you've been given a height here. After how many seconds after it was punted was it caught? So very similar to before. What I'm going to do is go into the graph, push tab. I'm going to enter another function. This function is just going to be a constant 5.5. I'm going to hit enter, and in this particular case we've got an intersection between the parabolic flight of the ball and of course a height of 5.5. So here's where you've got to use a little bit of common sense, and we've got to recognize that even though there are two intersection points, this first intersection point is when the ball is on the way up. And if you look carefully at the question, it expressly says as the ball descends. So when the ball is on its way down, when is it caught? And so clearly, or hopefully it's clear that what we're after is the second intersection point. So I'll go to my graph. I want to analyze graph. I want the intersection, and it's the second intersection point that I'm interested in. And that confirms, the 5.5 simply confirms the height at which the ball was caught, and the answer to the question at 2.74 or after 2.74 seconds. So 2.74 seconds after it was punted, it was caught at a height of 5.5. Okay, and then we have a possible scenario. If the ball were not caught, after how long would it have hit the ground? And so hopefully what you recognize there is what we're looking for is the x-intercept, the point at which the ball, which started at 2.5 feet, peaked at 34 feet, and has now gone down and hit the ground. And so what we need here is to analyze the graph and calculate a zero. Which graph, of course, because both of them may have zeros. I'm going to click on the parabola. That's the zero we want. Go to the left, go to the right, and there we have our zero, 2.867, which of course rounds to 2.87 if you're rounding to two decimal places. So after how long would it hit the ground? After 2.87 seconds is when the ball would hit the ground if it were not caught. Okay, hopefully that all made sense to you. The question which was not asked here, but I'll just make quick mention because we have a little bit of time, and that is what is the domain and range. And so hopefully you would be able to figure this out. We have a domain. Naturally, we're interested in time not being negative, so starting at 0 and ending in this example when the ball hits the ground, which is at 2.87 seconds. The range, which of course in the context of this problem represents the height. Even though the starting height is at 2.5, the ball does go back down and hit the ground at a height of 0, and so we must have 0 as our lower bound for height, and it reaches our maximum height, 34.14. And at this point you need to turn your attention to the assignment.